So welcome everyone. This is Digging Deeper, the Greenfields Prediction and 4D talk by Graham Begg. This is part of our monthly GSA SGEG Facets of Exploration webinar series. This is our talk. Usually we try to plan for the middle of the month. Our next talk would be, I think it's the 14th of August. So yeah, welcome Graham, and thanks for talking today.
Hey, thanks, Tim. That's good. Thanks for the invite to talk, and a little bit of background, I guess, on myself. I've been in the industry a long time. Quite a few of you I will know. Joined Western Mining a long time ago as a mine geologist in the Yilgarn. That was fun. And then exploration geologist in Eastern Australia. And then I was overseas. I ran exploration in Fiji, actually, for a couple of years around the Emperor Gold Mine, all the brownfields. And that's, we're talking about a Pliocene deposit. So that was fantastic to work on a giant deposit like that. I did my PhD on that deposit, and it's sort of a relationship to, the plate tectonic setting and all the way through to fluid processes. And then it was really a career that launched into the Asia Pacific and particularly porphyries and epithermals. But when you're in Western Mining, you were exposed to pretty much everything, most things. So you learn quite a bit about, nickel and zinc and these other things that the company was exploring for. So it was quite broad. And then it was a brief career in BHP for a couple of years when they took us over before I started my own company. And that was now 17 years ago. So that's time goes very fast. Over time, I became a project generation specialist, I guess. And about 20 years ago, or actually 22 years ago, we started an ambitious project to map the global lithosphere in 4 dimensions. And we partnered with Macquarie University to do that. So that work has continued in my company, and we've now got a global coverage of our 4-dimensional mapping of the lithosphere. So I'm going to talk to you about ore deposits. I should mention that my company, which was Minerals Targeting International, we're right in the middle of the process of changing the name to Litho Atlas Geoscience. That's going to be the new name going forward. Our products are used by most of the larger companies and a couple of smaller companies to help them with their project generation. So I'm going to touch on nickel systems briefly, and then in a bit more detail on the copper, convergent margin related copper, and also gold systems will be the focus. And maybe with a fair bit of this has been presented elsewhere. Some of it might be, a few little bits will be new with a bit of a twist. So I always start by looking at these diagrams because they provide the context for why we're doing what we're doing in terms of mapping the lithosphere in 4D. And on the left, you can see, we're really dealing here in these diagrams, mineral systems scale. It's not only whole lithosphere, but we're talking whole planetary geodynamic processes. So on the left, you've got a plume impacting thick lithosphere flowing to where the lithosphere is thinner towards the craton margin. That means that will the plume will decompress and melt most in that shallow setting. And so you margin related faults are active, then those melts can intrude and form our big Ni-Cu-PGE type deposits. And those melts can have variable interaction with the lithosphere, both the continental mantle and the crust, both of which can leave their signature and can be important to ore formation. On the right-hand side, with the convergent margin, we've got a modest dipping plate, relatively shallow dipping subduction setting. So that's impinging on the continent. You can see that it's thickening the crust in the arc environment here. And so where the ongoing plate reaches around 100 to 120 kilometres depth. In that general ballpark, the amphiboles break down, releasing quite a lot of water. So it stimulates melting in the mantle wedge. So this is how you generate ordinary arc magmas. When you have a compressive arc, Bob Laux has really nicely shown how the melt's trapped deep near the moho here, and you build up through repeated magma additions to this trapped magma chamber. You're getting ongoing fractionation of that chamber, so the volatile content builds up and up and up. And eventually that results in a very water-rich melt that can, when it does escape, when it does manage to escape, usually driven by tectonic change or a fault reactivation, then that very water-rich melt will lose its magmatic hydrothermal fluid quite deep. And because of the high water content, you get strong partitioning of copper into the fluid. So that's why you get these, grades of copper up around, like 1% in these deposits, whereas the grade of the copper in the actual magma down here is probably more like maybe 30 ppm copper, 40 ppm copper type values. And towards over here on the right, I'm showing a typical kind of scenario for moving gold and precious metals around. It starts with low degree partial melting in the mantle, and back arcs are kind of like the best place for this to happen, where you get lots of little bits of extension, little bits of heat, and little bits of fluid and melt coming up that can stimulate melting of alloys and sulfides in the mantle here. And that will sequester preferentially gold, platinum, palladium, tellurium, and copper into peroxenitic melts. Those small degree melts will then tend to accumulate in these metasomatized zones of the mantle and form little veinlets and zones of metasomatism. And that can be stored there indefinitely until you get the right trigger, usually tectonically induced, maybe decompression melting or a thermal plus or minus a thermal pulse, which will selectively melt those veins and give you gold. So that's the gold scenario. We'll come back to it. What these all share in common is transosporic faults connecting crust and mantle, geodynamic drivers, so the bigger scenario associated with whole mantle convection and plate tectonics and the like are actually preparing these systems. But the emplacement of the ores is generally caused by some sort of switch, quite often a tectonic switch, which then releases some, deep magma or fluid, so that it can end up forming deposits higher in the crust. Now, all of this is connected to supercontinent cycles, which is quite well articulated in a number of papers, I guess. We would land on roughly an 800 million year periodicity of the supercontinent cycles. And I'm going to show you just a couple of shots here that emphasize whole mantle convection. And this is a seismic image at a depth of about 1,000 to 2,000 kilometers depth. And so that's the middle of the mantle. The mantle's 3,000 kilometers thick, basically. So that's the flight from Perth to Melbourne. It's not that far away to the core mantle boundary, right? So interestingly, sort of halfway through the mantle here, the high velocity is the red-white color. You can see that will be the coldest things will have the highest velocity at this depth. And that, of course, will be a subducting slab. So you can see the Farallon slab here beautifully shown along the Americas margins. And if you use a simple reconstruction, it takes about 100 million years to get to this depth, okay, of a slab sinking very, very slowly through the mantle. If you look at a reconstruction of where the Americas were 100 million years ago, the West Coast is basically exactly under this point, okay? So when you subduct a plate, it ends up being vertically drawn to the middle of the Earth, center of the Earth by gravity, okay? The other things here are these are subducted slabs that predate the Africa-Europe collision, and these ones here predate the India-Asia collision. Of course, they've been sinking for 100 million years. The blue zones are the low velocity areas, and you can see they're starting to make two coherent regions here. These are these large low velocity provinces. This is the African one, and the little white dots or triangles and stars are modern day hotspots, which are mostly clustered either within or around the edges of those upflow zones. If we look at a cross section of seismic sections through the Earth, tomography sections, the color scheme is reversed here. So the slow velocity is now the red. And these nice images, I mean, for 20 years, there was a website, probably still exists, that was aimed at debunking mantle plumes. And really that was, I don't know, I don't really understand that. But anyway, partly it was caused by the fact that seismic tomography models were relatively low resolution. And a lot of that has improved a long way. And so that now we can very clearly image mantle plumes. These are, of course, the ones that form hotspots. You can see Samoa, and on a different section here, you can see three fingers, Samoa, Tahiti, and the Marquesas. And down here, you've got McDonald Island, you've got Pitcairn, you've got Cape Verde and Canary. So it's game over. It's definitely whole mantle convection. If we look at an image of the velocity at the core mantle boundary, here's these big blue, large, low velocity zones with the hotspots clustered around them. If we reconstruct where did all the large igneous provinces of the last 300 million years, where were they when they formed? And the causative plumes. So if we put an envelope around each one, you can see that they're mostly clustered in this region where we have this large low velocity anomaly today. Okay, now this is where Pangaea was. Pangaea formed by a long period of subduction, bringing the various continents and microcontinents together to form Pangaea. That process puts a lot of down around the core mantle boundary where it heats up. Some components of that become and the mantle plumes. And so they end up bombarding the base of the supercontinent and resulting in the mantle flow reversing and becoming overall an upflow. That upflow of mantle and aided by peripheral subduction around the edge of your supercontinent then breaks open the supercontinent. Okay, you disperse Pangaea. So everything's sort of connected, chicken and egg type fashion. These plumes have formed big deposits. So Norilsk, the world's biggest Ni-Cu-PGE deposit, formed when the Siberian traps erupted, and that was about here. The Skaregard PGEs and the relatively small Inciswa deposit down in southern Africa was here. So that's magmatic nickel. And if you look at that in terms of timing, that explains a lot of things. Like you can see here, we've got this is from our 2018 paper, 4 supercontinent cycles that are colored in the orange. And what you see is that most of the nickel deposits and the PGE deposits, the big ones, mostly form as you come into that peak of supercontinent. So this is when the most active collisions and is happening as you're building that supercontinent and as those big plumes from the core mantle boundary are starting to come up and bombard the base of the supercontinent. So it's a perfect storm for focusing melts. The best situation is the compressive settings where you've got a reactivated craton margin translithospheric fault system, and the very focused melts are more likely to form a big deposit. That's why you get this craton margin relationship, which is simplified here with the superior province, the Nain craton, various deposits of different ages. And then a figure from Pete Lightfoot's work just of the upper crust and showing how various staging chambers and our conduit network of these mafic, ultramafic intrusions interacting with the crust in various ways, sulfide saturation occurring and injecting batches of magma and magmatic sulfides, and then probably further sulfide saturation happening in some of those chambers as well, and then eventual settling of the massive sulfides. So very dynamic systems. And what we find is that the injection of those melts and magmatic sulfides into their final deposit environment is often, for the big deposits, it's often associated with some sort of stress switch, which is very interesting. And of course, transoceanic faults, your regional shortening directions and stress directions are going to determine which faults are most likely to be the conduits, or which fault environments. As I said, compression is best, focusing energy and focusing melts. And so in these sort of low MGO or mafic, ultramafic intrusive systems that you get a lot around the margins of these microcontinental and cratonic blocks, you see these stress switch situations, and we've documented a few of those in our 2018 paper. One thing to avoid if you're a project generator, keep away from margins that were close to a major ocean at the time of the large igneous province injection, because then subsequent collision is likely to destroy the deposit, or at least majorly downgrade it. Active subduction is also a negative. So a plume impacting a slab could be deflected and not really well focused in that environment. You want to be a bit more internal into the supercontinent and around those internal boundaries. So overall, it's the margins of thick lithosphere back within the continent or supercontinent in the more protected settings that are the sort of the perfect storm for forming a lot of these big deposits. We'll switch now to porphyries and gold, or copper and gold, if you like. And I'm going to articulate two processes. The first is the Laux process that we've named after Bob Laux for his seminal work on the porphyries. And the other one is the fume process, fertile upper mantle extraction, which is really about harvesting gold from the mantle. So first, let's focus on the left-hand side here, the Laux process, where ordinary arc melts in a compressional arc setting where those melts get trapped deep in the crust. They're building up extraordinary water contents, and eventually when that material does get an opportunity to escape, then you're getting fantastic partitioning of the copper with that very high fluid level, up to 14 weight% in some of these magmas. And so you get this massive upgrading of 40 type ppm to potentially 1% type copper values. And a cross section of one of those systems at the plate scale, you can see the relatively shallow dipping slab impinging on the continent and thickening the crust, trapping those melts. Now, as that water content builds up, it actually suppresses, with increasing fractionation in that magma chamber, it suppresses plagioclase crystallization and preferences hornblende and magnetite instead. So what you see is that then the strontium stays in the melt rather than go into plagioclase, and the yttrium goes into the hornblends instead of staying in the melt. So when the melt does escape, it's going to end up with a very high strontium yttrium characteristic, which is of what people call an adikitic melt. Okay, and that's the stuff that formed these big porphyry deposits. Bob's work nicely shows for the Central Andes, this is time on the x-axis, so 90 million years to present, and he shows the fluctuation of the strontium yttrium ratio of intrusions that are escaping and coming into the upper crust through time. And when you're in this late Cretaceous to mainly Paleocene orogeny, that's crustal thickening, you're trapping the melts deep. You can see the strontium yttrium of the intrusions is increasing. And when it finally releases because of a tectonic switch to more extensional or relaxed conditions, those melts escape. They end up forming these giant porphyry copper moly deposits. Similarly, during the incaic orogeny in the Eocene, you trap the magma deep, you build up the water content, the strontium yttrium characteristic goes up and up, up. Generally above something like 80 is where you get into the really nice productive magmas. And then you get a tectonic release, and you can see the whole system collapses as you're releasing these deep trapped magmas, and they result in a lot of big deposits, including supergiants like Escondida and Chuquicamata and the like. It happens again during the late Oligocene and the Miocene onwards, and we've reached this crescendo here of high and starting to get various intrusions popping up into the upper crust, releasing their fluids, and you're getting these supergiant deposits like El Teniente and lots of Facets and ones like that, the Bronces camp. And where is it? It's most likely to occur on continental margin arcs because you can sustain compression for long enough to keep this depth to really water content. It's a key thing. So we see this beautiful relationship of those sorts of arcs with the big porphyries. It can happen in an island arc. But generally, if you compress an island arc pretty strongly, it doesn't take long before some failure occurs of a margin, and that new subduction zone will relieve the compression or take up the strain. So you don't get to sustain the strong shortening as long. In these arcs that I've highlighted, these are good examples where the shortening was quite sustained for enough millions of years that you've got this fantastic fractionation build-up and eventually forming very big deposits. And the earliest one here would be the Jurassic of eastern China, the Jurassic to early Cretaceous systems, and of course the laramide of the western US and modern Andes. And of course, a modern day example is what's happening in New Guinea today with flat slab subduction under there, and you're forming very young deposits as a result. So what are you looking for? If you want to go back to a paleo example and you want to go through your exploration data and various stages of the modern system, what are the symptoms of these compressive arcs? You're going to look for things like fold and thrust belts, signs that you've had elevated topography, crustal thickening, ophiolite emplacement. So if the arc had been more of an extensional or neutral, let's say extensional arc, then there may have been oceanic plate material in the fore arc, and there may have been even in a back arc rift. So if you suddenly have strong convergence and shortening, that material is those settings are going to be inverted, and you're going to emplace ophiolites. Okay, you will see uplifted marine sequences because of the switch to compression. Foreland basins, particularly out in the hinterland behind your origin, you can see some very thick molasse basins in those regions. They're a symptom of that uplift and shortening. Regional unconformities, quite often angular, but you can even go back a long way inboard of the arc environment into your continent, onto your platform, and you will see very distinct unconformities in sedimentary basins that relate to these periods. So they're all indicators of what's happened in the past. Also, the sedimentary sequences will show a shallowing. As you squeeze sedimentary basins with shortening, they're going to shallow. So you might start off as deep marine facies, then shallow marine, and eventually fluvial conditions. The volcanism, if there is any, will be intermediate to felsic arc magmatism rather than any sort of mafic to intermediate, and you won't be seeing sort of intra-arc rifts. Subaerial volcanoclastics. So you're going to have a lot of topography and highly fractionated high viscosity magmas. So you're going to see a lot of subaerial volcanoclastics. And the arc axis is often going to migrate inboard, because with a shallow dipping subducting slab, the point at which the amphiboles break down and the big water release at about 100 to 120 kilometers, that point is going to effectively move inboard as the slab shallows. So the whole melt migration occurs so that the arc axis can shift with that. Shortening is really extreme, then the magmas are completely trapped, and you may see that there is no volcanism at surface. And so it's not an amagmatic arc, it's a non-volcanic arc. The magmatism is still happening, but it's being trapped deep at the moho in these big magma chambers. And a great example of that today is New Guinea. And if you look at the isotopic signatures of the zircons, you're going to see your epsilon, hafnium, and neodymium are going to really plunge down to very negative values as the trapped magmas deep in the crust are going to engage with that crust, melt some of it, and so you'll contaminate with that non-radiogenic material. Let's switch now to the fume process and fertile upper mantle extraction. So it's a multi-step process where you can build up these metasomatic zones over a long period of time. So little bits of melting, preferentially sequestering the gold and platinum group elements and tellurium and copper can end up in these little veinlets and from these proxenetic melts that are mobilized. And quite often there's a lot of CO2 involved in this process. Those veinlets then can be harvested if you have movement on these faults causing localized decompression melting. And so if you selectively melt those, because they'll have the lowest melting point, okay, they will tend to melt first, and they'll form alkaline ultramafic melts that'll be quite often very CO2 charged. Alkaline melts can carry order of magnitude or more CO2 than other melts, and that material can then come into the crust. Now, depending what happens to it in the crust, if there's one of these deep trapped magma chambers, you could blend with it and form a copper-gold system, because you're going to be bringing the metals with these melts into that environment. Or you could just blend with some other arc melts and form a sanucatoid. Or the lamprophyric melt could continue upwards, but because of its high volatile content, it's going to lose its fluid very deep, and then it will freeze. It won't continue upwards, and that fluid then migrates up to form, more like your orogenic gold type scenarios. And you can get everything in between. So you can get the intrusive related systems where some of those, melts do reach the upper crust. This is the famous example from Brent McInnes's PhD from near Lihir. So it was dredged from the seafloor, the Lihir Island and the Lihir deposit. 60 to 80 million ounces of gold. This glassy alkaline basalt casing this mantle xenolith is less than 1 million years old, and this mantle xenolith is highly altered. You can see the veinlet, and so this is one of these metasomatized zones in the mantle, and it's got various pyroxenes and sulfides, phlogopite, magnetite. In this one, quite often there'll be carbonates. So if you have some sort of decompression, remember there'll be trillions of tons of this material build up, and so when you have a decompression melt, the first thing to melt will be this veinlet. And if you melt lots and lots of these veinlets, you're going to develop a volatile, rich, alkaline, sort of lamprophyric type melt. Okay, and what we know from this work and other work is that the metals tend to be in these veinlets. That's where the gold and the copper is. It's not really in these wall rocks here. Okay, so you're selectively taking the metal, so you're upgrading in that process. I steered some researchers to a volcano in eastern Argentina and they sampled there and found mantle xenoliths. And these photomicrographs show that what they found in these xenoliths was that the metasomatized material was starting to melt, and it had formed these alkaline melts that then froze again and formed veinlets of glassy alkaline melt. So it was sort of like, and that those glassy veinlets have got free gold in them. You can see here, there's gold in olivine, there's gold in glass. This is gold in glass up the top. There's gold in sulfides as well. So in other words, this is the gold sort of caught in the act of being remobilized and starting to move towards the crust. And so if you have one of these triggering events like we saw in Eastern China, for instance, when you switched from strong compression to suddenly extensional conditions, then it's perfect for melting these little veinlets. So not only do you get this enormous gold province formed at this time in Eastern China, but in gold-rich province, and also copper moly deposits, but this gold-rich province. So basically all these little veinlets are contributing to every melt. So not only are they going to form lamprophyric little low volume things charged with metals, but they're also going to get caught up in any deeper basaltic melts that are coming up through those same structures. And so you can get basalts that form at the same time that are gold enriched, okay? Whereas these basalts here didn't form at a time that was conducive to adding in that melting of the metasomatized material. So those little veinlets. So these didn't harvest any gold, okay? And when you have these zones of metasomatism, they tend to be structurally focused translithospheric zones. And the effect of all the metasomatism and refertilization of the mantle root there will often cause the velocity to be a bit lower. So this is an image of the Superior Craton. It's a smooth seismic tomography image at a depth of around 200 kilometers with the high velocity in red. You can see the contours of the values. And in these lower velocity zones around the edge where all the structures are and all the metasomatism will be, that's where the gold ends up being formed, okay, the gold deposits being formed. Our work on the Superior would indicate that there was likely a subduction environment located well to the south of the Superior, in fact, south of what is now known as the Pinokian zone. And so these would have been back arc intracontinental rifts, okay, our greenstone environment. Come back to that later. Another symptom of having these metasomatic zones within the continental mantle is they can become quite conductive. So here we have the AusLAMP data from South Australia, really nice work done by the survey there. And this really strong conductor is at a depth of around 50 to 55 kilometres. And what it's doing here is it's following a very distinct structural corridor, which is partly, it's originally an old Platon margin, but then it gets reactivated as a back arc in the Paleoproterozoic. And then later on, you have a plume impact and reactivation, and you end up melting this metasomatized material. And it seems to be associated with the very enigmatic IOCG deposits. As you can see, Carapatina, Oak Dam, Olympic Dam, Prominent Hill, all on the margins of this thing, the Challenger gold deposit as well. If you look at the famous Hand of God section, it goes through about there and shows you the top sort of 180 kilometres of the lithosphere. And you can see the Moho dashed here. There's an offset here. Our mapping indicates that this is actually an Archean collision zone. It's reactivated a couple of times. As I said, the back arc rift in the Paleoproterozoic is one of them. And you have this plus plume impact at 1.6 billion years ago, and you're going to be melting some of this material here. It's coming into the crust, causing a lot of crustal melting. That's 40 kilometers across this thing, and a very conductive zone. And then you've got those pipes up to the deposits. So the whole system, it's big, and actually has quite a history to where you look at an area that you want to target for these copper and gold systems, particularly, let's say, former convergent margin or current convergent margin environments. Here, I use this very simple template as a good way to clarify your thinking. You've got a subduction zone here, strongly convergent and with orthogonal convergence, so that will really maximize the shortening in this segment of the arc. So you can see the wiggly lines, that's and crustal shortening. So if you're looking for the Laux type process of trapping that magma chamber deep, it's going to be along this sort of corridor here, on those big copper moly porphyry fertile magma chambers. That's roughly where they'll be. And then along that trend, of course, you'll have second order structures that are going to focus where they end up coming into the upper crust. I've highlighted a couple of examples of that where, in this case, very high angle translithospheric fault corridors, which, because of their tensile orientation relative to the shortening direction, they will tend to induce little bits of melting of the metasomatized mantle through decompression along their margins at depth. So you can cause that fume process that harvests the gold-rich material. And so you can not only get gold deposits along this corridor, think Porphyry, for instance, but those melts can blend with the deep magma chamber that's trapped at depth, and you can end up with a copper gold, porphyry like your Grasberg supergiant or your Octetes, etc. Okay, where the margin where the margin curves here because of the shape of the continent, the convergence angle it's much more oblique, and so or acute, and so what we're seeing here is more of a transpressional environment, sometimes transtensional, but in this case transpressional. So that's not so good for trapping these magma chambers deep. So you may get porphyry coppers up here in this type of setting, but they're going to be relatively low grade. But what they do have going for them is that this strike slip is fantastic for causing melting of the metasomatized mantle veinlets. And so you're adding gold, you're getting lots of gold systems, and you could get a copper gold porphyry, but just lower grade copper, or you can get gold only deposits of various descriptions. And this could be applied to the modern Andes. This could be Peru, in recent times, and up here, would be sort of like Colombia, Ecuador type situation, or you could apply it to North America during the Laramide orogeny, where this is, your southwest US with all the big porphyry copper moly systems, whereas the Canadian Cordillera is more this sort of setting, because you've got that curve of the continent, and so you're getting, lots of gold deposits and some copper gold porphyries. You could apply this if you inverted it to the Permian, the early Permian of the Central Asian orogenic belt in the South Tien Shan, where this would be Uzbekistan with full-on normal shortening. You get the world's biggest orogenic gold camp on a structure that runs perpendicular to that old paleo margin, with deposits along it. And whereas when you come to the east, you actually go into Kyrgyzstan and Tajikistan and southeast Kazakhstan, you've got lots and lots of gold deposits, along these sorts of structures at various intersections. So if we're going to embrace the full lithosphere in terms of mineral systems and how we target for them and understanding their geodynamics, then we better start mapping the globe in 4 dimensions as well. And we decided to do this actually in late 2001, our group, and we recruited Macquarie University as our partner because they understood the mantle and we didn't. And here we are, eventually I formed my own company, but 22 years later, the GLAM project has mapped the entire Earth at least once, and some places more than once. And this is an example of how you can use multidisciplinary data to see, well, where are these big structures on, craton margins and in these origins. And this is some nice work done by a Chinese group. And they show a cross-section. This is the seismic reflection line. The North China Craton is over on the left. Depth, the edge of the craton is actually this position here. You can see the moho inflection where the structure breaks through the moho. You can see the symmetries of the thrusting as you've crunched all of this together. And surface, we actually have a regional fault zone here. So the interpretation here, that's the Jianyang fault, and it's a regional fault with some strike slip components, so it must go straight through the lithosphere. And so it makes a lot of sense. Of course, seismic reflection can't image steep structures, so you have to infer them because of the patterns that you see and using other data types. And in this case, they've also got the magnetotellurics, and you can see this really nice conductor coming out of the continental mantle up this structure and into that position. There's a whole district of ore deposits in second-order faults of skarns and porphyries along this corridor. So what we're doing is we're mapping the surface of the planet. We've got about 6,000 crustal elements that all are characterized by their tectonic setting and their age and their composition. And we review the literature on every one of them. And then we also map what we call upper lithospheric domains at a depth of about 80 to 100 kilometers. That's below the crust, obviously. And I guess what we've discovered is that continents are segmented. They're very segmented into cratons and microcontinents. And quite a few cratons are composed of multiple microcontinents that coalesce to form that craton. Each of these have its own unique history. So by focusing on the events in the crust and what information we can get from these mantle roots, then we can see how the whole thing sort of talks to the whole lithosphere scale and map the connecting structures. And there are these very major corridors on the edges of these microcontinental and cratonic blocks. And then there are lots of other secondary structures that also penetrate into these roots and through them. But these corridors are the ones that really focus most of the damage, most partition deformation that you see in the crust, and are really great at focusing energy and ore deposits along those corridors. To do this sort of mapping, you've got to use all the geology and literature that you can, and the context of that geology that you can muster. The gravity and the mag, of course, the MT, the seismic data could be various types of seismic tomography are useful, different scales. That's passive seismic type methods, but it could also be seismic reflection and refraction profiles, or it could be receiver function data giving you detailed point information. And there's a lot of new technology being developed around seismic data. So it's very useful. And of course, we do also look at lots of geochemistry. So that's on both mantle and crust. We want to understand the signals in the geophysics that we're seeing in the mantle, and how can we relate this to the processes that we can see in the crustal history. This nice section I often show, the Western Gawler, Till and Heinsohn's nice MT section with the magnetics on top of the Western Gawler. You can see the big strike slip shear zones that bound the Fowler terrain. Now, if they're big strike slip shear zones, they have to be subvertical. There's a seismic reflection traverse here that, of course, just above the north of this line, that doesn't see those steep structures because it can't image them. And these structures have been mistakenly interpreted as shallow dipping. But if we look at other data, clearly subvertical, and this MT really shows it nicely. A nice conductor coming down to more than 100 kilometers depth here, another one over here. And that was only with 2 days of data collection that they did on this profile for each of their receivers. So if you're mapping your continent in third dimension, you're going to be mapping these blocks in the third dimension. And it's these corridors that are the corridors where most of the action gets focused. And that tends to be where most of the big ore deposits are going to be as well, is in those corridors above these points. Whether you're looking at the eastern goldfields of the Yilgarn, or you're looking at the modern Andes, or you're looking at pretty much every other terrain, and you're looking at magmatic and hydrothermal fluids. This is an example of our mapping that shows our ULDs, our mantle map at a depth of roughly 80, 100 kilometres. Ground is our proprietary seismic tomography developed at a depth of about 130 kilometres here, this image. To map these boundaries, we use the magnetics and the gravity data, the topography, and anything else that was available to us, as well as this seismic tomography. Sort of signature in our benchmark data generally is at this depth, indicates very depleted mantle compositions, in other words, poor in iron, very hasbagitic. And what we know from all of our work and our geochronology on mantle and crust is that these are Archean blocks, okay? And we have ages here, neodymium data going back to about 2.3 or so. Over here, there are actually Archean ages in the crust, both here and down here. So this is an example of one of these old microcontinents. It's got much younger crust on top of it, okay? So there's just little windows into some of that older crust, but mostly the crust here is actually Phanerozoic. The areas of lower velocity and these will be where the metasomatic melts have been focused and also capped. And hence that's where the ore deposits are. Okay, so the gold-rich ore deposits and even the big copper deposits in the region are in settings like this. So we've got a giant gold, a major, another major, giant, and another major. Actually, another giant just to the north of that structure there, in a newer version of this diagram. Northwest China is an interesting, well-endowed region of Central Asian orogenic belt. Of course, is well endowed, and it's Paleozoic arcs. And to the north of the Jungor Basin here, which is a flat sort of 500-kilometre cross desert, you've got the huge, mountains of the Altai, the mountains of the Tian Shan, smaller hills and mountains in the western Jungor and eastern Jungor. Mapping over here of the Paleozoic intrusions, arc-related intrusions, finds that there's actually an Archean diorite gneiss enclave within one of those intrusions. And drilling through petroleum, actually through this basin, goes into the Carboniferous basement, which is the red colour here. And the zircons there, the inherited zircons, were exclusively Archean. So Neo-Archean and Paleo-Archean, and quite a few of them euhedral to subhedral. So there has to be Archean basement in these locations. And the broader region around here, the zircons with their hafnium isotopes, if we plot age on the x-axis, epsilon hafnium on the y-axis, what you're seeing here is the typical sort of reworking trend of taking an Archean basement and remelting it, or combining young melts with the old basement to get this trend in time of the zircons. And then you've got your Paleozoic arc system, which is dominantly juvenile, because every magmatic arc spends most of its history in neutral to extensional conditions. So in those conditions, melts coming through don't see the old basement. They come straight through, they're juvenile, and you would never know the old basement is there. but occasionally some melts do engage with the old basement, particularly under periods of compression, when they sort of have to fight their way through the crust. So they're more likely to engage with the old deep crust. And so you get this mixing trend, this long tail of epsilon hafnium, between the reworked Archean type signature all the way through to the juvenile Paleozoic melt. So what the situation is here is clearly an Archean an Archean microcontinent, and that's why it's flat, and that's why the mountains are partitioned to its edges. Okay, and it's probably one of many of these blocks in this region. There is plenty of at least Paleoproterozoic aged blocks outcropping further to the west in Central Asia. Svalbard is on the Arctic shelf, and you've got the Archean down here of the Kola and Karelia and Norbotten cratons, with a little bit of reworking, of course, of the Norbotten craton. But you've got this shelf with Paleozoic rocks on it and a little bit of Proterozoic basement popping up. There are xenoliths coming up, volcanoes here, younger volcanoes, and they've sampled the crust, the deep crust, and that deep crust has evidence of an Archean basement with multiple overprinting events, including Archean and Paleoproterozoic and Mesoproterozoic, Neoproterozoic, as well as Phanerozoic. Okay, so by the time you rework the lithosphere that many times, its whole character starts to change, including its velocity response, its density, its geology, obviously, and potentially its metallogeny. And there's mantle xenoliths as well. The mantle xenoliths from here are Paleo-Archean with overprints. This is in situ rhenium osmium work on mantle sulfides. You can see there are overprints in the Neo-Archean, in the Paleoprote, the Rhodinian type stuff, and then down here in the Calidinide type age. An ex-Macquarie researcher with his student, Schettino, did a PhD student, did a fantastic job. They went and sampled volcanoes in central Mexico in the Sierra Madre. This is a defined sort of block with big structures on its edges. There's an inset here that shows some of these big structures. And there are a series of ore deposits along this margin, okay, of this block. Well, the in situ rhenium osmium on the mantle sulfides in these mantle xenoliths from these volcanoes gives a very clear Archean signature with a Paleoproterozoic overprint, Rhodinian overprint, Pan-African overprint. Similarly over here, again, the Archean signature, big Neo-Archean signature, sort of fairly, Paleoprote, like Eburnean type signature, Rhodinian, etc. We know there's quite a bit of old crust kicking around towards the south. It's at least Mesoproterozoic. Everything south of that here is Gondwanan and comes from the top of South America. This is the only place in Mexico where this quality of data actually exists. So you've got to ask yourself, is it likely to be just serendipitously the only Archean block that gets detected? I would say that's extremely unlikely, and that Archean lithosphere and old blocks of Archean lithosphere are strewn all the way through here. Okay, so just to sort of start winding up, we'll switch to a bit of geodynamic context. And I mentioned about the Superior Craton. Our work indicates that if there was a convergent margin, it had to be at least south of the Pinokian block, which means it's a long way back to where your greenstone belts are. They are way interior, far intracontinental back arc rifts. And so your arc environment has been basically destroyed subsequently by Proterozoic overprinting and subsequent younger rocks. So if this is what our Archean cratons potentially looked like, then we will never solve the issue of Archean subduction by just looking at this environment here, because the melts back here are not going to be classic arc type magmas, okay? But you've got to look at the whole system and the context regionally and all of the factors here, and you say, it kind of makes sense. And I can apply this sort of thing to lots of Archean cratons. So it's just a cartoon version, how we would sort of think about the Yilgarn. The early phase, if there was subduction, then it would be the perfect way to pull apart these intracontinental rifts, forming greenstone belts along them. You've got the plume impact forming the nickel, and then you start to shovel everything back together again with a series of collisions that explains the switches of shortening that you see, the triggering of the fume process to form the big orogenic gold deposits. And after a few multiple collisions building a supercontinent, you end up frozen into your Knorrland or Archean late Archean supercontinent. My last example is the Tasmanides, and this is from our work and showing a reconstruction of, you can see the outline of Australia here. It's the thin line coming down. Of course, it was joined to Antarctica. This is 107 million years ago. So Antarctica, there's the outline of Antarctica. And these are all old microcontinental blocks. New Zealand is basically made of this bit of the Campbell Plateau and this bit of the Challenger Plateau and a couple other bits. And what we've been able to ascertain here is that there is a lot of evidence of Archean lithosphere in here. We're just doing a bit more due diligence on this bit up here under Lord Howe Rise. But there's very strong evidence elsewhere, the purple bits being evidence for Archean, both mantle and crust. And of course, this piece here is the bit that breaks away, forms Zealandia, and you end up with the Tasman Ocean, which is about 2,000, or a bit less actually, kilometres wide between them. But we should rethink how we view these Phanerozoic origins like the Tasmanides, which is normally depicted as juvenile growth of an origin. What we would strongly dispute that and say that actually it's crammed full of old microcontinents that have been segmented, opening up multiple oceans that are sequentially closed by subduction and collision, hence all the switches and various tectonic events you see in the Tasmanides. And of course, it triggers and controls orogenesis, mineral systems and the formation of, quite a lot of ore deposits. So I'm going to leave you with this final slide that ore deposits are produced obviously by mineral systems, their lithosphere scale. It's intimately linked to the global geosystem. And the geodynamics preps the system, causes those magmas to be trapped deep to form that fertile, water-rich magma chamber for the porphyries. It helps you mobilize little low-degree melts to build up gold-rich source regions. If you take this sort of approach, you only need one model to explain gold deposits. It's what happens to it after you trigger and harvest it that matters in terms of the sort of deposit you end up seeing. And that all is dependent on multiple factors that are on that pathway to the upper crust. And then what we see is that it's the architecture that determines where these occur, and that is full lithospheric architecture, and it's generally stress switches, real regional changes that trigger the emplacement of the best ore deposits. So I'm going to stop there. Thanks.